Welcome to the AI Research Roundup. I'm Alex. Today, we are looking at a paper from the Hugging Face trending list, published on November 14, 2025, about 5 days ago. It introduces an open research agent that adds interaction scaling as a third axis beside model size and context length. And in tests, the 72 billion parameter version reaches 81.9% on Gaia, 37.7% on HLE, 47.1% on Browse Comp, and 55.6% on Browse Comp ZH. The paper is titled MiroThinker, Pushing the Performance Boundaries of Open Source Research Agents via Model, Context, and Interactive Scaling. And, as we will see later, the idea of scaling interaction depth has really intriguing implications for how we train research-grade models. Also, the author shared a full GitHub repo for MiroThinker. Inside, you'll find the official code for the research agent and MiroFlow framework, model variants, tool and agent configs, a 5-minute quick start, environment and API key setup, plus scripts and configs to run benchmarks and reproduce their results. On Hugging Face, you can grab MiroThinker's 8 billion, 30 billion, and 72 billion parameter research agent weights, with examples for long context, tool-augmented reasoning, and multi-step, multi-tool workflows. Figure 1 shows that MiroThinker's largest model consistently ranks near the top against both open and commercial research agents across several demanding benchmarks. The grouped bar charts compare average scores, so taller dark blue bars mean stronger research performance. In humanities' last exam, Browse Comp, and Browse Comp ZH, MiroThinker trails only the strongest closed systems, while on GAI, Xbench Deep Search, and Seal 0, it actually leads all open options. Figure 2 explains how the research agent actually operates as a tool-using system. The left side shows the tool interface, which bundles the Linux sandbox, file management, and web search tools that the model can call during reasoning. The central block covers context management, which keeps only the most recent and relevant tool outputs so the 256,000 token window stays efficient. On the right, the stacked think, tool call, and tool result boxes depict a long multi-turn interaction, where older, less useful turns are gradually omitted while the agent works toward a final answer. Figure 3 shows how the team actually builds the data that teaches the research agent to reason with tools. This figure illustrates two pipelines, both feeding into the same robot agent, which then supplies data to a final evaluation pool called Miroverse. The top row starts from curated public datasets, passes them through a quality filter and a verifiable check, and only then accepts successful items. The bottom row starts from messy raw internet data, turns it into a concept graph, which is a network of related ideas and entities, and then refines it with a data engine before the same accept or reject step. Table 1 spells out how different tools using foundation models stack up across the same research benchmarks, so it grounds the earlier charts in raw numbers. The table lists commercial systems like OpenAI GPT-5 High beside other strong baselines, and reports their accuracy on each benchmark. These scores show that the best closed models still lead on tough tasks, such as humanities' last exam, GAI-A, and WebWalker QA, which sets a very high bar for an open research agent to approach. This table highlights how strongly the three MiroThinker versions compete against both tool using foundation models and prior research agents on each benchmark. The shaded rows at the bottom show that even the smallest 8 billion model already matches or beats many earlier agents, which signals that interaction scaling helps at model sizes. The 72 billion model then pushes accuracy close to the best commercial systems, especially on GAI and Browse Comp ZH, so the open agent genuinely narrows the gap. Figure 4 shows that after reinforcement learning, the agent confidently uses more interaction turns and, as a result, solves tasks more accurately. The top row plots how often different turn counts occur, comparing supervised fine-tuning in blue with reinforcement learning in purple, which shifts the curves toward deeper interactions. The bottom row gives the same story as cumulative probability, showing that reinforcement learning trajectories more often reach higher turn counts. Together, these plots say that interaction scaling really works. Training the agent to sustain longer think and tool call cycles consistently boosts benchmark performance. Alright, wrapping up, 2 takeaways stand out. Interaction depth emerges as a real, third scaling axis, alongside model size and context length, and a carefully trained open research agent can now rival top closed systems on demanding multi-step tasks. The broader implication is clearer deep research for everyone. That is it for this episode of the AI Research Roundup. I am Alex, thanks for listening.